Okay, we've got a few extra minutes, so we'll start off with, who knows what Burning Man is? Good. This presentation is going to be a talk of how I ended up at Burning Man. At the end of the day, this is what I was involved with building with a whole team of people. It started off basically by a desire to go to Burning Man, but one of the main principles of Burning Man is that you contribute to Burning Man. There's 10 major principles. The one thing I had at the time in 2014 was I had my long service leave. So I had 3 months of leave to use up, and I decided I'd spend about 6 weeks of it contributing to a large art anything that was going to be at Burning Man. There's a couple of hundred art exhibitions of different sorts at Burning Man each year, and there's about a dozen or so are really large, apart from the man themselves and the temple as well. So what I did was I went to a place called the Box Shop in San Francisco, which is a art cooperative down in the more industrial sort of city side of town. It's a large sort of mixture workspace storage facility where artists can contribute to any art they want to work on. It gives you access to a workshop. There's storage facilities for storing work in progress. And we'll see a bit of that in the video that shows. So this was the concept. Now, the artist Jessica Welts, San Francisco born welder. So she's worked as a machinist and a welder for many years, and she'd been inspired by the movie Labyrinth. You can see in the top left here, there's this large sort of model of the solar system that was part of the movie. It's in the movie for about a minute or two. And that gave her an inspiration for what we see on the right there, which is sort of a realisation of something similar that's functional as well. Now, in the movie, the model of the solar system moved and rotated to some extent. Jessica's vision was to have one that was to scale. So the planets would actually orbit around the sun at the scale rate. So we'd have Mercury rotating around in 20 seconds, and I think Neptune went around in 14 hours. So there were some challenges there. Obviously we needed the sun to be on fire, this being Burning Man. That was a contribution as well. We also wanted the planets to be realistically and representatively scaled in diameter, and to have some of their moons around them. They would also orbit as well. In the end, we had to make compromises between art and science. Obviously, the size of it wasn't to scale, or we'd end up with Neptune a couple of hundred kilometres away. Now, Jessica needed a lot of people, and this was one of the most complex projects we've ever actually made at Burning Man. Many of the art is stationary, so it'll be a large sculpture, people can climb on it. Some of them might rotate, and you can also climb on those that rotate. However, this was complicated in the way that we had many moving parts in it as well that moved at different speeds. So it's not the largest thing that's made at Burning Man by a long shot, but it's probably one of the most mechanically complicated. Next. So the way we did this was initially Burning Man also gives arts grants out to various artists who are working on large projects. Jessica managed to get an arts grant of about $22,000 US, and then we decided we also needed a Kickstarter as well. So this is the sort of the front page from the Kickstarter, one of the sort of a quickly knocked up 3D model of roughly what it might look like. And the description there is a 16-foot tall kinetic steel sculpture of our solar system representing the majestic dance of heavenly bodies. It was going to have a lot more dancing in the way we could program it to go to different orientations of planets. That never eventuated for a reason you'll see why. So starting off with the design here. These are some of the sketches that I made. Now I got on board in May. I was due to go over to the US at the end of July. I was there for 4 weeks when we'd build this thing, and then we'd install it with a basic manufacture time of building of 1 month. The design time was part-time by a handful of us. There's a couple of engineers involved. There was another guy who was involved in the major gearbox we'll see. I was involved in a lot of just the conceptualisation of how we make large planets revolve around the sun. This is large to the extent where lots of people can walk underneath it while it's actually moving as well. And so we don't actually want it to topple onto people either. and it is very windy where we were going as well. Burning Man's in the middle of a salt lake. We get large dust storms and winds up to probably 80 to 90 kilometres an hour occur pretty routinely. So there's a little bit of environmental load on that. There's also, as I mentioned, very dusty. So this thing gets totally coated in an alkaline dust. So we also had to design for along the line of can it survive the environment it's in. So we had a central column, we needed some arms to rotate around it. Initially looked at using some lazy Susans as a sort of a concept of how to get something large to rotate. We also looked at assemblies using skateboard wheels. Did some maths, the skateboard wheels wouldn't have survived. Some of the loads on the wheels were about half a tonne because of the large cantilevered arms we had, and they only went up to about 100. So we went for some industrial lazy Susans we managed to get. There was also 4 much lighter assemblies for the inner rocky planets. So there's the 4 rocky planets, and then there's the outer gas giants. The larger outer planets were also going to be hollow, they had to glow from the inside as well as rotate, just to add to the challenge. So for the inner rocky planets, we went with a large set of 2 metre diameter gears to drive it all. We also had, so this is a rough sketch, so you can see we've got Mercury, Venus, Earth and Mars there. Earth and Mercury needed to have some moons rotating around them as well at a reasonable speed. So in this case it wasn't scale, no one wanted to wait 28 days to sort of see the moon go around the Earth. And so we basically chose times that would be sort of interesting and doable with sort of mechanics that we had access to. We had to work out how to stack and reuse some lantern gears, which were generally last used a few hundred years ago for driving windmills in Europe. We converted that concept into making them out of steel, basically because they're very tolerant of poor fits, lots of gravel and rubbish in the way, self-cleaning and a few other things like that, rather than the normal gearing we see these days. For the planets going around, this is the sort of design we did. Basically, sketchbook design, we would come up with, on the left is the basic concept. Okay, we need the moon to go around the Earth. We can do it with the moon, sun, planet system, some gears. And then you actually work out how to support it all, hold it, how to actually make it work as a thing. Bearing in mind, in this case, the Earth was also a glass-blown sphere that was hollow inside that needed to be lit as well from the inside while it was rotating. The moon wasn't too bad, it was just the moon. And so we'd start off with sketches, we'd then convert these into proper designs because we did have access to laser cutters, water jet cutters and also CNC plasma cutters as well. And so we could convert these into 3D models, convert those into 2D cutouts for use of the very CNC machine. And this is what you see when you run things through SolidWorks. So in the top left there is the basic steel frame. That's about 2 metres across at the bottom, 1.5 metres high. The right picture there is one of the arms that goes out. They varied in length depending on which gas giant it was representing, from being about 3 metres long to about 6 metres long, if I remember at the end. And the bottom base sort of shows some of the initial concept of how we'd have these large gears rotating around for attaching to it. And the other fun thing, this was all done in imperial measurements as well. So I was lucky to be going through school in the days when we had imperial and metric. So, and as my time as an engineer, I also had to deal with that as well. So I was actually familiar with working in both at the same time. The whole thing was basically done in imperial at the end of the day, being in America. So we converted the rough sketches into models. So we had a handful of people who were doing some modelling using SolidWorks. The other thing from this, we'd get cutting lists as well as purchase lists as well. And a lot of the design guides these days will give you 3D models of bolts, motors and things. They can be imported into something like SolidWorks. That can then go into a purchase list as well to help make things sort of more automated. We could also export all of this into cutting sheets for the plasma cutting. We were cutting through 6 foot by 8 foot sheets of steel pretty much on a constant basis for a couple of weeks using the plasma cutter, running probably between 6 and 12 hours a day. There was a phenomenal amount of steel cutting into this. I don't know what the total weight was in the end, but it needed cranes to assemble. Yep. So this is what fabrication looked like. So luckily, like at the bottom left there, you can see one of those main arms actually ended up looking like it was designed, which is always a good sign to actually see those things appearing. The top left there is when we start assembling it. You can see we're actually in the largest workshop. We're needing to use cranes and fork trucks to lift this thing together. The bottom right there is some of those 2-metre diameter large gears that rotate around the central column, driven from the inside. Now, the range of skills we used was quite large in this project. Apart from the basic metalworking skills, which was Jessica's forte, we also needed some large planets up to a bit over 1 metre in diameter. These you can't buy. It's very hard to buy large diameter translucent spheres. So we CNC machined moulds out of foam. These were then sanded, and then we used those to cast our own translucent planets. And then Jessica's sister did the painting on the planet. So here's Jupiter. And all of the gas giants had a similar effect where they were translucent fiberglass. There was going to be lighting on the inside to light them up at night. And we then put a clear coat just to sort of protect it from the environment to some degree. All sorts of lessons to be learned there with how to release spheres from moulds. And I think it took a couple of attempts before the sort of casting team managed to get that one right. And these are some of the other skills needed in something this large. We have the electronics. So I did the electronics design, the lighting design. So we used Arduinos and some motor controllers for rotating each of the planets on the end of each arm. Each arm had its own power supply with a large capacity 12-volt battery. There was also plans on having an I2C comms bus running down for varying the lighting and having it remote controlled. In the end of the day, we ran out of time for that. That'll probably happen the next time it's used. There was mechanical assembly with the gears and the gearing, where we had to, using the one motor, drive the rotation of the planets at one particular speed, and the moons at a different speed as well. So that was done using differential gearing, driving off the one shaft. All of these were just from kit robotic parts as well, so just to make it easy to assemble. The Earth itself, one of the people who was the painter, was actually, as a side hobby, does glass blowing. So basically the Earth you see there is a flat sheet of glass that has been coloured with coloured glass and then basically blown on the inside of a mould to give that particular Earth. So that's a solid but hollow, solid piece of one cast glass that was blown inside a mould with the map of the Earth already on the glass to give it that final effect. That was the painter's sort of minor skill, which pretty much is one of the most amazing things I've ever seen as well. So now we'll go to a little video that was made.
I've got my energy drink
just before we left.
My snack.
Back. So when we were over there, one of the local newspapers, one of the San Francisco newspapers, decided to do an article on
I've
this.
got my energy drinks and my snacks, and I'm ready to go. I'm just going to keep going until the truck gets here. I'm working on a Burning Man project. The project's called Celestia Mechanica. It's a model of the solar system. The idea comes mostly from me being sort of a space nerd. I originally started welding when I was very young and worked in the welding industry, and I was also an artist, and so now in this time of my life I finally have a chance to sort of take the two disciplines, and so I'm doing welding, artistic welding. I was picturing it in my head and everything seemed small and manageable, and now after we're seeing it all come together, it's like, wow, this is more daunting than we initially thought.
So I've only been with the shop for 2 major projects, but from my understanding, this might be one of the most complicated projects that's ever come out of here. There's still like a lot more work to be done, and it's supposed to get in the truck tonight. It's do or die mode.
A lot of people are already out in the desert right now. We're coming in a little late. That's okay, because ours is a kinetic sculpture. It's very complicated mechanically, and so we have like a bunch of engineers actually who have been working on this really hard, but it's a daunting process. There's a lot of moving parts to make 8 planets spin around. I've always been kind of a person that does things on my own and with my art, and so this is sort of the first time I've been running a crew of people, and so it's really just incredible management experience. Having an idea on paper that you've been staring at drawings of, and then all of a sudden there it is, it's real. It's one of the most satisfying things that have experienced. Yeah, there's an end in sight. I see it happening very soon. It doesn't matter because whether we're done or not, we're going to put it all in that truck.
So the last bits you saw there weren't actually Celestia Mechanica, they were one of the other projects that was being built at the box shop at the time. So from there we had a 55-foot box truck semi-trailer taking our art and a couple of other projects out into the desert, plus a lot of the camping gear, a lot of the food and water, all sorts of things like that. You have to be self-sufficient. And we were going to be there for about 11 days assembling this. The environment out in the desert is harsh. Showering is rare, maybe once a week. It's hot and dusty during the day, it's chilly at night. We still had to design things like the length of the fencing runs. They were to be done on site. And there's no loop, so no filings, cuttings, cable tie bits, anything allowed to be left behind. So you've got to tie it up completely behind you. So installation. So this gearbox that had 40-something sets of gears inside of it was all driven off one motor to make all of these things go around. Never been tested before. We did have a failure with that at some point. These are some of the photos from the assembly. So it becomes pretty tricky at using slightly heavier equipment, cherry pickers, lifters and things. You've got to have a large work tent as well for storing and organising all your tools or equipment. Even things like the counterweights had to be made on site. Took 5 days to be assembled. Here's a picture as we get the sun on. We hadn't run the propane pushers yet, but that was a minor particular issue. And some of the final assembly going together here. There's some planets being assembled, put online. We never run the arms together, so we didn't even know if the planets missed each other as they went past. That was a late design aspect of it, as in on-site. They missed nicely. We had to have lighting towers organised for working through the night. And we just finish off with a couple of photos. So this is basically shows what it looks like at the end of the day. So the sun's on fire, the arms are rotating around, the planets are lit up from the inside, and the moon's going around the planets. And we literally had thousands of people coming around. There's also other things like the fencing around it to keep people away so they don't catch on fire. That itself has things like cast meteorites and asteroids were cast and put onto it. And there was lighting in a few other places as well. There's a daytime shot of it, what it basically looks like in the daytime after the first dust storm with a nice layer of dust over it. See it in the stationary shot. Another shot giving a bit of a close-up with the rings that used to light up at night around the planets as well. The motor driver unit at the end, and in the background the main tyre, the main drive. And that's it. So each of those items, you could probably do a 15-minute talk on either the planets or the arms or the gearbox or the lighting or the electronics, or even just how to get it logistically out there and how to organise fork trucks, cranes, cherry lifts and the whole lot, and lighting at night. One of the largest projects been involved in. I used to be an engineer in a previous career, and this is probably as complicated as many large projects I've worked on. The difference being we did entire manufacture, assembly and installation in 4 weeks. For this particular project, and the design was basically part-time design. None of the people were practicing engineers. Everyone who contributed skills were basically just makers. And one thing that enabled us to do this was actually having a facility in San Francisco called the Box Shop, which gives us access to computer CNC plasma cutters, lathe machines, storage and things like that. And so sort of the infrastructure is really important for doing large art projects, and hopefully we'll be able to see some of that in Adelaide in the forthcoming years. Thank you.